So the topic of today's lecture is conditional expectations, okay? So you kind of should know that this was coming because we spent last time talking about conditional PDFs, and so the natural next thing to want to do is to take expected values, right? So last time we talked about things like, I could have a conditional PMF if I'm in a discrete random variable, or I could have, that was like the goofiest curly F, like this, conditional PDF if I'm in a continuous space. And like I said, as I go forward, you're probably going to see me slipping a little bit more on really being hardline about curly F instead of P for PDF. It's all the same thing, really. I mean, PDF and PMF are basically the same idea. So the idea is that, I give you a value of X, and then I ask you, okay, how does that change the distribution of Y? And if those two variables are not independent, then there will be some sort of change, right? I'll have some sort of knowledge that X gives me that will change how Y looks, right? And so now, once we've got these PDFs, I can do all the stuff that I usually do with PDFs, things like expected values and means and variances and functions of random variables and stuff like that. So now we can compute for example, in the discrete case, I could ask for the expected value of some random variable given that I observed this random variable would be something like I sum over all the possible values of Y the probabilities, the PMF values of these conditional pieces of the probability mass function. Or if life was continuous, what I would do, I'm sorry, there's got to be a Yj here. That's important, right? This is the part that actually gives me the expected value. In the continuous world, I would say, okay, I observed this value X, and what I do is I integrate over all the possible Ys the conditional PDF like this. So either I'm adding or I'm integrating. And clearly, this is like a function of the random variable. So both of these are going to be functions of the given value of X. Right? So I'm not going to get a number here. I'm going to get a function of X, right? Because clearly this expected value depends on whatever that value is. So that's the basic setup. So I should actually pause from the very beginning about questions about this. Okay, so now I could ask, okay, so this is like a conditional expected value. It's going to be a function of X. And so now I could ask, okay, if I think about this as, think of this as a function g of x equals the expected value of y given x, right? So this is a mapping from a number x to some function, which is the expected value of y given x, okay? And now I could ask, I could ask, what is the expected value of g of x with respect to x, right? So x has also got its own PDF, right? So I could ask for basically what is the expected value of this function of x, which is the same thing as basically like it's a double expected value. What the heck? So let's work out what this means, right? And we're going to come to an answer that is hopefully intuitive, right? So, and let me preview what the answer is so kind of we know where we're going. So basically, the idea is saying, here I give you some expected value of y given x, right? And I take the expected value of that. Kind of what I think should happen is that I should just get the expected value of y, right? This is like saying, first I kind of condition on x to give you some expected value of y given that. And now I kind of take the expected value again over all those possible values of x. What I should get is kind of like just the expected value of y in the first place. And that's what I'm going to do. So let me just prove why that's true. And then we'll talk about why it's useful, because it seems like this is a more complicated thing to do. So what is the expected value of, if I define this function here, g of x, that's like saying I would take the integral of this function that I care about of x, and then I multiply it by the PDF of x, right? That's how I compute the expected value of any function, right? And I'm leaving off, I mean, all these integrals are like minus infinity to infinity, but it makes life easier if I don't have to put that everywhere. And I defined this g of x as the expected value of y given x. Then I have this PDF. So now let me think about what is this piece here. This piece here is exactly what I would get by just plugging in this formula, right? This piece here is going to be an integral, and then an integral inside this integral, which is y times this conditional PDF dy times this PDF dx, right? So all I'm doing is I'm plugging in what I learned over here into this guy. And now I'm going to rearrange things a little bit. I'm going to say, okay, I'm going to switch dy and dx. So I'm going to do dy afterwards, which means I can take the y out first, and then I can have this integral, which is going to be f of y given x, f of x like this, dx, dy. And now what I get is, you know, we talked about last time how I could decompose, this is like the conditional times the marginal. And then what I get is the joint PDF, right? That's like saying I have this thing here times the overall joint PDF. That was kind of like an outcome from last time. This is equal to the joint, which is this guy. And now this is saying, what happens if I integrate the joint out, dx? That's like saying, well, I don't care about x, I just care about what's happening in a fixed value of y, right? So what I get here is y times the other marginal, right? This is the marginal in y that comes from integrating this thing out. And then this is just the equation for the expected value of y. So this is actually a nice little sequence of steps to make, you know, I mean, if you're not clear on exactly what happened here, this is a good thing to practice on, right? So we leveraged a bunch of things, right? The definition of expected value, the property that conditional times marginal equals joint. And then we ended up with this basic result, which is that the expected value of y given x is what we came up with as the expected value of y. This is called the law of iterated expectation, or yeah, expectations. So, as I'm going to show you in just a second, often this is more convenient than trying to estimate the expected value of y by itself. As I can show you, there are some problems where it's really messy to figure out, like, what is the PDF of y directly if I'm giving you, you know, some pieces of marginals and joints. And in practice, you know, it's a lot easier to just say, okay, I know what the conditional PDF is, and then I just take the expected value of that again, and I get the double expected value. So I'll do some examples where hopefully that will become a little bit more clear, okay? So let me hold questions for a second until I do an example, and then we can talk about it, okay? So let me do the example right now, since I promised you the example. So let's just do a quick example of the coin flipping from last time. So here, x is the number of heads in 3 flips. Y is the position of the first head, 0 if no heads. And then I can make a table of the joint PMF, right? So the joint PMF looks something like this, where if this is my x and this is my y, I have possibilities 0, 1, 2, 3 here, 0, 1, 2, 3 here. And then, as we recall from last time, the PMF looked like this. And if you look, oh, I'm sorry, if you look back at your notes, you should find this table. For example, the probability of getting 0 heads and 3 flips is 1/2 cubed, so that's 1/8, and then there's only one, then there's only one value for y, right? Similarly, the probability of getting 3 heads is also 1/8, and then the first head has to occur on that throw. If there's only one head, there are 3 ways that can happen, and the head could be in any of the 3 positions with equal probability, right? So this is kind of from last time. And now what we could do is look at the conditional expected values. So first of all, let's look at the conditional PDF, right, or PMF. So the conditional PMF of y given x, right? So this is like the joint PMF. Now what I'm going to do is I'm going to make a similar looking diagram, but what I'm going to show here is P of y given x. So again, I have the same possible values for x, and I have these possible values for y. And the way to read this is kind of along the rows, right? This is like saying, okay, if x was 0, what would the conditional PDF of y be? Well, it's like saying, okay, well, if this happened, then I normalize this row by the sum of probabilities, and in this case, I would have a normalized PMF that looks like this, right? Because it's a certainty that if 0 occurred for x, then 0 must be the value of y. If 1 occurred for x, well, then I take this row and I normalize it by the total probability, which is 3/8, right? So it's like saying this can't happen, and each of these things has a probability 1/3 of happening. In this case, this can't happen. This has probability 2/3 of happening. This has probability 1/3 of happening, and then I have a certainty in this case. Right? So each of these things, adds up to 1 because these are all themselves new PMFs, right? So if I want to compute the expected value of y given, say x equals 0, well, it would just be 0, right? It would be a certainty. If I want to compute expected value of y given x equals 1, it would be 1/3, well, I guess I can just write down, 1/3 times 1 plus 1/3 times 2 plus 1/3 times 3, and this gives me 2, right? The middle value is 2. Expected value of y given x equals 2 is going to be 2/3 times 1 plus 1/3 times 2, which is equal to 4/3. And the expected value of y given x equals 3 is just 1, right? So those are the conditional expected values. And then if I wanted to apply this law of iterated expectations, this is like saying, okay, now what if I want to figure out the overall expected value of y, right? The overall expected value of y is, by this rule, the expected value of y given x with respect to the x distribution. So this is like saying I have 0 times the probability that x was equal to 0 plus 2 times the 2 times the probability that x was equal to 1 plus 4/3 times the probability that x was equal to 2 plus 1 times the probability that x was equal to 3. And now I have to remember what were these probabilities, right? This again is the number of heads in a coin flip, so the marginals here we know are 1/8, 3/8, 3/8, 1/8, right? So I can solve this as 0 times 1/8 plus 2 times 3/8 plus 3, plus 4/3 times 3/8 plus 1 times 1/8. So what do I get? I get 6/8 plus 4/8 plus 1/8 is 11/8. Okay? And I can verify that if I look at the marginals in y, right, the marginals in y would have been what I got if I were to add up this way. The marginals in y, this is like 1/8 probability, this is like 1/2, 1/4, 1/8, right? So direct computation would be to say, okay, I've got 0 times 1/8 plus 1 times 1/2 plus 2 times 1/4 plus 3 times 1/8. So I get 4/8 plus 1/2 is another 4/8 plus 3/8. It's the same 11/8, right? So it checks out. The system works. So this is just an example to show that, in fact, yes, you know, things work as I proved that they had to work. So I got the expected value of y in 2 different ways. One was directly evaluating it, and one was going through the double expected value. And at this point, you're asking yourself, well, why would I ever want to do the double way? And I'll show you an example of that in a moment where it turns out to be a lot easier to compute it that way. But let me stop and ask, so questions about this example or the big picture? Okay, so let me do this now in a continuous example, okay? So let's now do another example we talked about last time, which was, this is like the continuous example from last time. Which was the following. I pick x as a uniform random variable on 0, 1. And then I pick y as a uniform random variable on the interval 0 to x, right? What is, well, first let me ask, what is expected value of y given x? Well, this is pretty easy, right? This is like saying that, I'm just going to evaluate it out. Well, first of all, what is the PDF of y given x? I think we talked about this last time. That's just saying I have a uniform distribution on 0 to x, and so the height of this uniform distribution has to be 1 over x in order to integrate to 1, right? And so I can already see, I don't even have to do any computation, that the expected value of y given x is the middle value of the distribution, right? I mean, if I wanted to be really pedantic about it, I could say that expected value of y given x is equal to, I would integrate y times the conditional PDF of y given x dy, right? And y here would range from 0 to x. And so I would have 1 over x times 1/2 y squared from y equals x to y equals 0. So I'm going to get 1 over x times 1/2 times x squared, which is the same x over 2 that I could get from the picture, right? So, I mean, I didn't have to do this, you know, integral. I could just look at the picture, but I can show that the integral is still the case, right? And then I could ask, so then, what is the expected value of y, right? So last time, we did a lot of work, you know, to figure out what was the marginal PDF of y. We found out that the marginal PDF of y was minus log y when y was in this range. So if you look back at your notes from last lecture, we came up with this, right? So if I wanted to compute the expected value directly, I would have to do this, right? Minus y log y dy. Now this is an integral that I don't know how to do, or at least I don't want to do it on the day before Thanksgiving break, right? Because this is going to be some sort of integration table or integration by parts. Certainly on an exam you face this, you're like, well, I don't know what to do with this, right? But now I can use the law of iterated expectation to say, well, all I could do is I could take the expected value of y given x, right? What did I learn over here? I learned that the expected value of y given x was x over 2. Which is basically going to be the integral from 0 to 1 of x over 2 times the PDF of x. Well, PDF of x is just 1, right? dx. So what do I get? I get 1/4 x squared at x equals 1, x equals 0, and I end up with 1/4, right? How easy was that? So computing this in this roundabout way was actually a lot easier because the conditional was particularly easy function, so it wasn't a hard time to get this, and then taking the expected value of that was, again, like immediate. So life was much easier than trying to evaluate this, which I could do, but will come out to 1/4 in the end anyway, but it'll be a lot messier to do, right? So that's kind of, a little bit of a motivation for, why instead of, this would be like integration table or integration by parts or something like that. We don't want to do that. So that's kind of the motivation, is that many times, just like last time, right, or even on the homework where you had a conditional thing, I said, okay, there's this setup with Yaz and Ryan, and they're screaming, and I tell you what their conditional PDFs are, right? The conditional PDFs are very easy to do. The joint PDF might be more complicated because it's the sum of two Gaussian functions, but I don't have to go through a lot of hoops to figure out the overall expected value because I could just say it's, these two things put together, right? So I think this is, the lesson for today, and you're going to see on the homework examples of easy or mostly easy computations of expected values using this iterated expectation rule. And I'll ask you to double check that you got the same answer that you did get in the homework when you did it in the more tedious way. Okay, so comments or questions about this? Just to take that Yaz and Ryan example very quickly in a different way slightly. So another example of this would be to say, okay, suppose this is just like a different gloss on the two Gaussians, right? So suppose that I have a binary communications channel where the input is either 1 or -1, and the output is whatever I got plus some noise, where this noise is Gaussian with mean 0 and variance sigma squared, okay? So in this case, I can see that, if x is 1, so basically I can kind of do a quick sketch of what happens when x is 1. That's like shifting the Gaussian to have mean 1 and variance sigma squared. If my x is -1, that's like a Gaussian with mean -1 and variance sigma squared. And so if I want to know what is the expected value of y overall, it's going to be like the expected value of y given x equals 1 times the probability that x equals 1 plus the expected value of y given x equals -1 times the probability that x equals -1. And in this case, these are just the conditional means, right? The expected value of y given x equals 1, by definition, is just this 1, right? It's like 1 times this, and then it's plus -1 times this. So it's just the difference between basically these, you can think about these like prior probabilities. I mean, I could have asked you this in the context of the Doctor Who problem, right? As well as the expected value of the frequency that you hear, right? And it would be basically like a weighted combination of Yaz's mean frequency and Ryan's mean frequency, right? Another example, which I'm not going to work through in a lot of detail, is, this is just like a handy formula to know. So In fact, I'm not really sure why I'm putting this down here right now. Well, I could put it down here. So basically, just for reference, I think we talked last time about conditional Gaussians, right? So if we have jointly Gaussian random variables in the most general sense, right? So, I have mu x, mu y, sigma x, sigma y, and rho. That's what I need to define my two-dimensional Gaussian random variable, right? So it turns out that the conditional mean is given by this formula. And this is just really for having it written down somewhere. Don't worry about this too much. So we kind of talked about this last time in the sense of I made my life easier. I said that these means were equal to 0 and these sigmas were equal to 1. And in that case, what happened was that my conditional mean was equal to rho sigma y and, I'm sorry, rho x, right? That's what I get if I plug everything in. And my sigma was equal to 1 minus rho squared. We kind of, just mentioned that last time. This is like the more general form of that, right? And then I can see that, the expected value of y given x is just, well, this is all constants. So basically what I'm going to get is where did I get tangled up here? So the expected value of y given x is mu. That's right. I said if I want to look at the expected value of y, it's like the expected value of y given x. And what do I get is the only random variable here in the expected value of this is x, right? When I take the expected value of that, I get mu y plus the expected value is mu x minus mu x times this complicated junk. Doesn't matter because all this stuff goes to 0, right? And I can see that I just get the mu y again, as I know I have to, right? Okay, so let me do another example. I don't really have anything to talk about today other than examples of this common theme, right? So again, kind of instead of, oh, sorry, question. There is no rho sub x, right? So it's, oh, I'm sorry, you're talking about this? This is like rho x. No sub x, just rho times x. And that should be in your notes from the last lecture too. Okay, so let's make this a little more back to less messy equations, right? So here's an example that's kind of more like an insurance or health example, right? So life expectancy. I think we did an example like this in pre-exam 1 days, or life expectancy. And actually, you can imagine that if you were an actuary, you'd be doing these kinds of conditional PDF things all the time, right? So you kind of want to know, okay, given that this is the distribution of my customer base, and these are the probabilities of different diseases given this customer base, how much should I charge them for insurance, right? So there's actuarial science is just like one big conditional PDF problem, right? So just with a twist, so let's say that x is the age of a randomly selected person. Which we're going to say is uniform on 20 years to 70 years. And then y is the years left to live. I'm sorry, this is a grim example. for a person of age X. And let's say that is exponential with lambda equals 1 over 80 minus x, okay? So let's think about this. This is just kind of like saying that, you know, if you were 20, the conditional PDF is exponential with mean 60, long time to live. If you're 70, then the conditional PDF of years left to live is mean 10, which kind of makes sense. The older you are, the, you know, unfortunately, less years you have left to live. So that means that the conditional PDF of y given x is like some sort of exponential PDF, but my lambda is this, you know, function of x. So for positive values of y and for x in the range 20 to 80, or so 20 to 70, I'm sorry. So by definition, the way I set this up, the expected value conditionally of y given x, well, what's the expected value of this exponential random variable? It's 1 over lambda, which is 80 minus x, right? And then the expected value of y for the whole population, and this is like, now I'm taking into account the distribution of my ages, is like the expected value of y given x. So now I integrate over x, going from 20 to 70, of this expected value here is 80 minus x, and then my PDF of x is 1 over 50 dx, right? Because this guy is just uniform on 20 to 70 and has to be of height 1 over 50, right? And now this is a pretty easy integral to do. It's 1 over 50 times 80x minus 1/2 x squared at x equals 70, x equals 20. I could plug in my numbers and do my math. What I would come out with would be 35, right? So that would be the average amount of time that would be the expected value of years left to live irrespective of age, right? Kind of taking into account the age distribution of people. So questions or comments about this? All right, let me do one more example, and then I think we're going to be pretty much done. So last example is kind of like, again, let's look at this interplay between Poisson and exponential. That's something that we talked about a little bit, and let me just kind of try to remind you of those things. So here's another example where let's let t be the time required for customer service. Okay, so let's imagine that this is like a bank or something like that, where people are coming up and they're being serviced, right? So let's suppose that this is exponential with parameter alpha, okay? And then let's let n be the number of customers that arrive for service in an interval or during an interval of length t. Right? And we're going to assume that this is Poisson with parameter beta t, right? So beta is kind of like my underlying persons per minute, and then if t is the number of minutes, I expect there to be bt people coming through, okay? So these kinds of problems come up a lot in electrical engineering problems in the context of queuing and packet arrivals and stuff like this, right? How long does it take me to deal with problems, okay? And so I might want to ask, for example, okay, what I'm kind of telling you here is this is like the conditional distribution of n, right? But now I may want to know, okay, what's the expected value, or what's the expected value of n, right? What's the PDF of n? I want to know what's the probability that 3 people arrive while someone else is getting dealt with, right? And this kind of, again, comes back to how many people do I need at the security checkpoint in the airport, or how many people do I need at the bank to handle customers, right? So let's kind of write down what we know, right? So we know that the PDF of t is exponential with parameter lambda, right? So this is going to be the PDF of t. T is going to be a continuous random variable. And I know that by definition, the expected value of t is 1 over alpha, and the variance of t is 1 over alpha squared. How do I know this? Because I looked it up in the book. Or at least we proved this a while ago, right? So you've been using this already. This is something that you'd find in that table of common random variables, right? What does the second part tell me? The second part tells me that, okay, now I have a discrete random variable because I can't have half a customer, right? So I have a discrete random variable, which if I'm going to be really strict about it, is a Pmf, right? The Pmf of the number of customers given I tell you what the interval is something like it's Poisson with this parameter, right? So it's like saying this is the Poisson Pmf from before exam 1. Right? And so here, this t can be anything, this n can be 0, 1, 2, 3, whatever, right? So in some sense, kind of what I have is a mix of continuous and discrete stuff. Now, the expected value of n given I tell you some value of t is going to be just the mean of this distribution, which I know already is beta t, or I guess in this case it's beta capital T because my t is over here. And then the variance we also learned from the table long ago turns out also to be beta t. So this is kind of like from definitions of Poisson. And now I can ask, what is the expected value of n overall, right? So what is the expected value of n, right? What is the expected value of the number of customers that are arriving during my turn at the bank, right? Well, the expected value of n is going to be the expected value of n given t, right? I'm doing this, again, this law of iterated expectation, because what I gave you was the conditional distribution, right? And so this is actually pretty easy. It's like saying, okay, well, the expected value of, I just wrote this down, beta t, and I know that this is going to be beta over alpha, right? I don't have to do any integration because I know this already. I just took the beta out. That's easy. What is the variance of n? Well, that's going to be the expected value of n squared minus the expected value of n squared. And now I need this, right? So again, I'm going to use the same law of iterated expectation. And I guess I didn't really explicitly say it, but let me say it here. You know, the expected value of n squared, I can basically plug in any value of, or any function here and do this iterated rule, right? Same kind of idea. So here, what I'm going to get is, well, I have to actually do this integral, I guess, right? Expected value of n squared is going to be, actually, I guess I have to go through this. So here, the conditional expected value here is going to be beta t plus beta t squared, right? It's like the mean. It's going to be the, this is like a mess to write, but basically, you know, just like this, the variance of x is equal to e of x squared minus e of x squared. And now I'm going to move this over here, so I get the expected value of x squared is equal to the variance of x plus the, plus the mean of x squared. That's exactly what I'm doing here is I've got the variance plus the mean squared. And now I have to integrate this with respect to my PDF of t, whatever that is. And again, I don't actually have to do a lot of math here. So this is like saying this is going to be equal to beta times the expected value of t plus beta squared times the expected value of t squared. And then I come back to here and I say, okay, back to variance of n. This is equal to expected value of n squared. We just figured out that was beta e of t plus beta squared e of t squared minus what is the expected value of n squared? It's going to be, I just figured this out somewhere. It's going to be beta squared e of t squared, like this. So I should get basically, I get this part is the variance, or I'm sorry, this part is the expected value of t. This part is the variance of beta squared times the variance of t. The variance of t I can compute from my guy over here as 1 over alpha squared. So I get beta over alpha squared. So why did I go through this mess, right? So kind of what I'm trying to say is that here's the idea. So I computed the expected value of this was a certain number, right? And the variance of this was some other number, okay? Now, let's suppose that, the mean of this n is always equal to whatever this number is, right? If the variance of t is equal to 0, right? So that's like saying that, suppose that there was absolutely no variation in the waiting time per person. They all took exactly 5 minutes every time, right? So in that case, the variance of t would be, that's like saying the expected value of t would be some constant, and the expected value of n would basically be beta times whatever that constant is, right? And the variance of n would be whatever variance came from just the innate variation of the Poisson random variable, right? So this is basically just like a Poisson random variable where there is nothing to worry about in terms of the variation of service time, right? If t is not random, if t is not deterministic, so if t is random, then what we find is that the expected value, or the variance of n, is equal to kind of some base value plus something times the variance of t, right? So, the more variation in t, the more variation in n. Right, that kind of makes sense because variability in how long it takes me to get served can only make the variability in the number of people coming during my session go up, right? I can only be less certain about that value. So again, this is kind of a messy example to end on. I'm not really sure why I chose it, but this is the idea is that, you can solve these, somewhat complicated setups without having to go all the way to the joint PDF, right? So I think the lesson for today, the key takeaway, which is basically the only thing that we did today, was that if I have the expected value of some function of y, that sometimes it's easier to get there by looking at that function of y conditioned on some other variable, okay? So This is like kind of, you know, whatever function we want. And that it's often easier to go through this double expectation than it is to compute that directly, right? Because otherwise, you know, suppose that all I gave you was the joint distribution, right? So I might have to integrate this complicated function against some complicated joint distribution and come up with some number, whereas it turns out sometimes to be easier to take these extremely simple conditional distributions and take the expected values of those, right? So again, think back to the example of the life expectancy, right? I had two uniform distributions that were both very easy to compute, whereas the joint distribution of that would have been a little bit hairier. It would have been this weird thing over a triangle like we talked about in previous lectures. So that's all I want to really get at today, is that this is, you know, all you have to remember from this whole hour-long lecture, okay? Okay. Questions or comments? All right, so we only have a few lectures after break, right? So maybe there's 4 or 5, and like I talked about, you know, those are getting into some of the final things that you really have to know about probability, as well as some beginnings of machine learning kind of stuff about, again, maximum likelihood, Bayesian, stuff like that. So have a good Thanksgiving, and we will see you in a week.